January 21st, 1968, 15:45 hours Greenland time. Thule Air Base Control Tower, 750 miles north of the Arctic Circle. Air traffic controller. Captain James R. Shepard watched his radar screen as a single contact appeared 200 miles south, tracking north toward Thule at 35,000 feet. Hobo 28, Thule Tower, we have you on radar. What is the nature of your emergency? The response crackled through static. Thule Tower, Hobo 28. We have smoke in the cabin, declaring emergency. Request immediate clearance for approach and landing. Shepard checked his notes. Hobo 28 was a B-52G Stratofortress on Chrome Dome patrol, a routine airborne alert mission. Smoke in the cabin was serious but not uncommon, electrical fire most likely. The B-52 was robust, the crew was trained. They would make the approach, land safely, deal with the fire on the ground. Standard emergency procedure. Hobo 28, you're cleared for emergency approach. Runway 10, winds 270 at 15 knots. Fire crews are standing by. What Captain Shepard didn't know, what the calm voice of Major Tully on Hobo 28 didn't convey, was that the smoke was not from a minor electrical fault. A catastrophic fire was consuming the crew compartment. The pilot and co-pilot were already wearing oxygen masks, struggling to see through smoke so thick it obscured their instruments. 3 crew members in the lower compartment had minutes, perhaps only seconds, before toxic smoke rendered them unconscious. And what neither Shepard nor the crew of Hobo 28 knew was that in 7 minutes, the B-52 would crash onto the Arctic ice 7 miles short of the runway, disintegrating on impact, scattering 4 B-28 thermonuclear bombs across the frozen sea ice, 2 of which would have their conventional explosives detonate, contaminating the ice with plutonium and creating the most dangerous nuclear weapons accident in a populated area. Captain Shepard watched his radar screen, monitoring Hobo 28's descent. A routine emergency, fire trucks waiting, runway clear, everything under control. He had no way of knowing that in the burning B-52 descending toward Thule, a crew was fighting for their lives, and that the Arctic ice was about to become contaminated with weapons-grade plutonium that would take months to clean and decades to fade. The smoke over Greenland was not routine. The emergency was not under control. And the 7 minutes Hobo 28 had before impact would not be enough. To understand how 4 nuclear bombs ended up scattered across Arctic ice near one of America's most important Cold War bases, one must understand Chrome Dome, Thule Air Base, and the strategic context of January 1968. Operation Chrome Dome, as described in previous incidents, kept nuclear-armed B-52 bombers airborne 24 hours a day along routes near Soviet airspace. By January 1968, Chrome Dome had been operating for 8 years. Approximately 12 B-52s were airborne at any moment, each carrying thermonuclear weapons. The specific route flown by Hobo 28 was designated Chrome Dome Route 1, depart from Plattsburgh Air Force Base in New York, fly northeast over Newfoundland, across the North Atlantic to Thule Air Base in Greenland for potential emergency landing, then northwest along the Greenland coast, across the Arctic Ocean parallel to Soviet territory, then south back to Plattsburgh. Total flight time, approximately 24 hours. Mid-air refuelings, 3. Thule Air Base was critical to this operation. Located at 76.5 degrees north latitude, 750 miles north of the Arctic Circle, Thule was the northernmost American base. Its 10,000-foot runway could accommodate B-52s. Its radar systems provided early warning of Soviet bomber or missile attacks over the North Pole. The base housed approximately 3,000 American military personnel and 2,000 Danish and Greenlandic workers. The strategic importance of Thule extended beyond Chrome Dome. The base hosted the Ballistic Missile Early Warning System, BMEWS, a massive phased array radar capable of detecting Soviet ICBM launches at ranges exceeding 3,000 miles. BMEWS was America's primary defense against surprise nuclear attack from the north. If Soviet missiles flew over the pole toward North America, Thule would detect them first. In January 1968, the Cold War was at a particularly tense point. The Vietnam War was escalating. The Tet Offensive would begin on January 30th, 9 days after the Thule incident. Soviet-American relations were strained. Nuclear arsenals on both sides exceeded 30,000 warheads. The doctrine of mutually assured destruction meant any nuclear exchange would be catastrophic. Chrome Dome existed in this context as both deterrent and liability. Deterrent because Soviet planners knew American bombers were always airborne, ready to retaliate. Liability because bombers carrying nuclear weapons were subject to accidents, and accidents involving nuclear weapons near populated areas or sensitive locations could have profound consequences. By January 1968, Chrome Dome had experienced several serious incidents. The Palomares accident in Spain in 1966 had scattered 4 nuclear bombs, 2 of which contaminated a Spanish village with plutonium. The Goldsboro incident in 1961 had nearly resulted in a nuclear detonation in North Carolina. But no Chrome Dome accident had occurred at a location as strategically sensitive as Thule. The B-52G Stratofortress that crashed at Thule was tail number 580256, one of 193 B-52G models built between 1958 and 1961. The aircraft was 9 years old in January 1968, relatively young for the B-52 fleet. It had accumulated approximately 9,000 flight hours and had been maintained according to Strategic Air Command's rigorous standards. The B-52G carried a crew of 7 on Chrome Dome missions: pilot, co-pilot, navigator, radar navigator, electronic warfare officer, and 2 gunners. For the January 21st mission, the crew consisted of Major Curtis R. Tully, pilot, Captain John Haug, co-pilot, Major Frank Hopkins, navigator, Captain Richard Marks, radar navigator, Captain Leonard Svitenko, electronic warfare officer, and Master Sergeants Calvin Snap and Robert Snyder, gunners. The weapons load consisted of 4 B-28FI thermonuclear bombs, each with a selectable yield between 70 kilotons and 1.45 megatons. For this mission, the weapons were set to their maximum yield of 1.45 megatons each. Total destructive power aboard Hobo 28, 5.8 megatons, or 387 times the Hiroshima bomb. The B-28 was a relatively compact weapon, 13 feet long and 20 inches in diameter, weighing approximately 2,000 pounds. It employed a 2-stage thermonuclear design with a plutonium fission primary and a lithium deuteride fusion secondary. The weapon could be delivered by parachute or in freefall mode, with altitude-fused or contact-fused detonation options. Critically for the Thule accident, the B-28's safety system included a thermal battery that required manual arming before the weapon could achieve nuclear yield. SAC regulations for Chrome Dome missions prohibited fully arming weapons during flight. The thermal batteries were not activated, meaning the bombs aboard Hobo 28 could not achieve nuclear detonation even if their conventional explosives were triggered. However, the conventional explosives in the bombs, designed to compress the plutonium core, could detonate under certain conditions. If this occurred, the plutonium would be dispersed without nuclear yield, creating radiological contamination. This scenario, known as a plutonium dispersal accident, was precisely what would occur at Thule. The mission of January 21st began routinely. B-52G tail number 580256, call sign Hobo 28, departed Plattsburgh Air Force Base at 13:42 hours Eastern Time on January 21st, 1968. The takeoff, climb, and initial cruise phases proceeded normally. The aircraft headed northeast toward Newfoundland, then across the North Atlantic toward Greenland. At 14:30 hours Greenland time, 13:30 hours Eastern, approximately 6 hours into the mission, Hobo 28 completed its first mid-air refueling over the North Atlantic. The tanker boom operator reported normal operations. The B-52 took on 110,000 pounds of fuel. No problems were noted. At 14:45 hours, Hobo 28 passed over Greenland's southern coast and began its leg north toward Thule. The aircraft was at 35,000 feet, cruising at 450 knots. Estimated time to Thule, 45 minutes. At 15:30 hours, the crew noticed smoke in the cabin. The source of the smoke was later determined to be the crew compartment heating system, specifically a cushion on or near the aircraft commander's seat. The B-52's cabin heating system at high altitude used bleed air from the engines, ducted through heat exchangers. A malfunction in one of these heat exchangers, combined with flammable materials in the cushion, initiated smoldering that rapidly developed into open flame. Major Tully, seated in the left seat, was the first to smell smoke. "I've got smoke here," he announced on the intercom. Within seconds, smoke became visible, filling the upper flight deck. Captain Haug, the co-pilot, immediately activated the smoke evacuation system, opening vents and attempting to clear the cabin. But the smoke intensified. Within 2 minutes, it was so thick that Tully and Haug could barely see their instruments. At 15:32 hours, Tully made the critical decision. "We're declaring an emergency, heading for Thule immediately." He banked the B-52 left, turning northeast toward Thule Air Base, now approximately 150 miles away. At their current speed, they would reach Thule in 20 minutes. But 20 minutes assumed the aircraft remained controllable, and already the smoke was affecting the crew's ability to function. Tully and Haug donned oxygen masks, but the smoke obscured their vision. The lower compartment, where the navigator, radar navigator, and electronic warfare officer sat, was filling with toxic smoke from the heat exchangers. At 15:34 hours, Tully established radio contact with Thule Tower. His request for emergency landing clearance was calm, professional, following protocol. But in the cockpit, the situation was deteriorating rapidly. The smoke was not just obscuring vision, it was becoming toxic. Carbon monoxide from the burning materials was accumulating in the cabin despite the oxygen masks. At 15:36 hours, Captain Marks, the radar navigator in the lower compartment, reported difficulty breathing even with his oxygen mask. The smoke was so thick that the crew's oxygen supply was being compromised by smoke particles clogging the mask filters. At 15:38 hours, Tully made a second critical decision. They would not make it to Thule with a normal approach. The fire was intensifying. Visibility was near zero. They needed to descend immediately and land as soon as possible, even if that meant an emergency landing on the ice short of the runway. At 15:39 hours, Hobo 28 began an emergency descent. Tully pushed the nose down, decreasing altitude from 35,000 feet toward 10,000 feet at maximum safe descent rate. The goal was to reach an altitude where the crew could bail out if necessary or attempt a crash landing on the ice. At 15:40 hours, 10 minutes after the smoke was first detected, the lower compartment crew reported they could no longer see their instruments. Captain Svitenko, the electronic warfare officer, was showing signs of smoke inhalation, coughing continuously despite his oxygen mask. At 15:41 hours, Thule realized they would not make Thule. The smoke had defeated them. Vision was impossible. Control of the aircraft was becoming compromised as smoke affected the pilot's cognitive function. They had one option left: evacuate the crew and abandon the aircraft. At 15:42 hours, Tully gave the order: "Prepare to eject. Bailout sequence on my mark." The B-52's ejection system was complex. The pilot and co-pilot had upward-firing seats. The 4 crew members in the lower compartment had downward-firing seats. The process required precise timing to avoid crew members colliding during ejection, but Hobo 28 was not in a stable flight condition for ejection. The aircraft was descending through 12,000 feet in smoke, so thick the pilots could not see to maintain attitude. The descent rate was excessive. The aircraft was not level. At 15:43 hours, Captain Svitenko, in the lower compartment, collapsed from smoke inhalation. Captain Marks attempted to assist him, while simultaneously trying to position himself for ejection. At 15:44 hours, Tully, realizing the crew would not survive much longer in the smoke-filled aircraft, ordered immediate ejection. "Eject! Eject! Eject!" Captain Haug, the co-pilot, pulled his ejection handle. The canopy above his seat blew off. Explosive charges fired his seat upward into the Arctic sky. The seat separated at 8,000 feet. His parachute deployed. Haug would descend onto the ice, injured but alive. Major Tully ejected seconds later. His ejection was successful. He reached the ice alive. In the lower compartment, the ejection sequence was more complex. The 4 crew members had to eject downward, through the floor. Captain Marks ejected successfully and survived. Major Hopkins ejected successfully and survived. Master Sergeant Snap ejected successfully and survived. Captain Svitenko, unconscious or semi-conscious from smoke inhalation, did not eject. It is unclear whether he was unable to reach his ejection handle or whether he was too incapacitated to pull it. Master Sergeant Snyder, the remaining gunner, also did not eject successfully. One or both may have been incapacitated by smoke. At 15:45 hours, 6 crew members had successfully ejected. 2 remained aboard. The B-52, now unpiloted, continued its descent toward the Arctic ice. At 15:46 hours, the B-52 impacted the ice approximately 7 miles southwest of Thule Air Base runway. The aircraft struck at a shallow angle, traveling at approximately 300 knots. The impact forces were catastrophic. The fuselage broke into multiple sections. The wings separated. Fuel tanks ruptured. Over 150,000 pounds of JP-4 jet fuel spilled onto the ice and ignited. The fireball was visible from Thule Air Base, a massive orange glow in the Arctic twilight. And somewhere in that burning wreckage, 4 B-28 thermonuclear bombs separated from their mounting points and were scattered across the ice. The crash of Hobo 28 was witnessed by personnel at Thule Air Base. The fireball was visible for miles. Within minutes, rescue teams were dispatched, helicopters launched, emergency procedures activated. At 15:50 hours, the first rescue helicopter arrived at the crash site. What they found was a scene of devastation. The B-52 had disintegrated across approximately 1,000 feet of ice. Burning wreckage was scattered in a rough line following the aircraft's impact trajectory. Smoke from burning jet fuel rose hundreds of feet into the Arctic air. The primary concern was locating survivors. The helicopter crew spotted parachutes on the ice near the crash site. They began recovery operations immediately. Within 30 minutes, 6 crew members had been located and recovered. 5 were injured but alive. Captain John Haug had suffered severe injuries during ejection and died before reaching medical care. The bodies of Captain Leonard Svitenko and Master Sergeant Robert Snyder were located in the wreckage. Both had died in the crash, having failed to eject or having ejected too late. But as rescue operations proceeded, a more serious problem became apparent. The B-52 had been carrying nuclear weapons, and those weapons were now somewhere in the burning wreckage on the Arctic ice. At 16:20 hours, Thule Air Base Commander Colonel Frank Duffy received confirmation that Hobo 28 had been carrying 4 thermonuclear bombs. He immediately notified Strategic Air Command and activated nuclear weapons recovery procedures. The incident was classified as a broken arrow, the military term for an accident involving nuclear weapons. By 1700 hours, specialized nuclear weapons recovery teams were being mobilized from bases across the United States. But they faced a problem. Getting to Thule in the middle of Arctic winter, with 24-hour darkness, sub-zero temperatures, and limited daylight, would take time. The teams would not arrive for at least 12 hours. In the meantime, local personnel from Thule began the dangerous work of securing the crash site. The priority was locating the 4 nuclear weapons. In a fire hot enough to melt aluminum aircraft structures, with jet fuel still burning, finding and securing 2,000-pound bombs scattered across ice was extraordinarily difficult. At 17:45 hours, the first bomb was located. It was approximately 200 feet from the main impact crater, lying on the ice. The weapon's casing was damaged but intact. There was no indication that its conventional explosives had detonated. Recovery teams established a perimeter and began planning how to move the weapon to a secure location. At 18:30 hours, the second bomb was located. Unlike the first, this weapon showed evidence of high explosive detonation. The bomb's casing had been blown apart. Plutonium components were visible among the debris. The weapon had undergone a one-point detonation, where the conventional explosives initiated, but the nuclear physics package did not achieve criticality. The result: no nuclear yield, but plutonium dispersal. This was the nightmare scenario. Weapons-grade plutonium, one of the most toxic substances known, was now scattered across the ice near Thule Air Base. The contamination area was unknown. The amount of plutonium dispersed was uncertain. And in the 24-hour Arctic darkness, with temperatures at -30 degrees Celsius, assessing the contamination was nearly impossible. At 19:15 hours, search teams located debris from what appeared to be a third bomb. Like the second, this weapon had experienced high explosive detonation, more plutonium contamination. The situation was worsening. At 20:45 hours, after hours of searching, recovery teams had accounted for 3 of the 4 bombs, 1 intact. 2 with their conventional explosives detonated and plutonium dispersed. But the 4th bomb remained unlocated. Search operations continued through the night, but finding a 2,000-pound weapon scattered across square miles of ice in darkness, with contamination concerns limiting search efforts, was proving extraordinarily difficult. By morning on January 22nd, 16 hours after the crash, the 4th bomb had still not been located. The possibility emerged that it had broken through the ice and sunk into the sea below. The ice at the crash site was approximately 6 feet thick. The impact of a 2,000-pound bomb falling from a disintegrating aircraft traveling at 300 knots could potentially penetrate that thickness and reach the water. If the 4th bomb had sunk, recovery would be difficult or impossible. The water depth near the crash site exceeded 500 feet. Visibility in Arctic waters was near zero, and the window for recovery operations was limited as the ice would begin breaking up in the spring. The recovery operation that followed the Thule crash was one of the largest nuclear weapons accident responses in history. Over the next 7 months, approximately 1,700 American and Danish personnel worked to clean up the contamination, recover weapon components, and remove contaminated ice and debris. The Department of Energy's Atomic Energy Commission deployed specialized teams to measure radioactive contamination. They found plutonium contamination extending approximately 2,500 feet from the main impact point. The highest contamination levels were concentrated in areas where the 2 bombs' high explosives had detonated. The cleanup strategy was straightforward, but extraordinarily labor-intensive. Remove everything contaminated. This meant cutting contaminated ice, loading it onto vehicles, transporting it to a secured area, melting it, and shipping the contaminated water back to the United States for disposal. By February 1968, 1 month after the crash, workers had removed approximately 10,500 cubic yards of contaminated ice, snow, and debris. The material was placed in 6,000 barrels and transported by ship to the United States for disposal at the Savannah River plant in South Carolina. But the work was dangerous. Plutonium contamination required special protective equipment. Workers wore multiple layers of protective clothing, respirators, and dosimeters to monitor radiation exposure. Despite precautions, several workers received measurable plutonium exposures, though none exceeded safety limits. The search for the fourth bomb continued through the spring of 1968. By April, as the ice began breaking up, the recovery teams concluded that the weapon had likely penetrated the ice and was resting on the seafloor approximately 500 feet below. In May 1968, the Navy deployed deep-sea search equipment, including divers and sonar, to search the seabed. The operation, codenamed Project Crested Ice, searched for 3 months, but did not locate the missing weapon. By August 1968, the search was suspended. The official conclusion was that all 4 weapons had been recovered or accounted for, with 3 weapons definitely recovered and the 4th probably recovered in fragments that were not separately identifiable from other debris. But this conclusion was controversial. Some personnel involved in the recovery operation believed a complete weapon remained on the seafloor. Documents declassified in 1995 suggested uncertainty about whether all weapon components, particularly the secondary stage, containing highly enriched uranium and lithium deuteride, had been recovered. The question of the lost bomb at Thule remains unresolved. If a complete weapon or significant weapon components remain on the seafloor near Thule, they represent a potential environmental hazard and a security concern. Corrosion over decades could release plutonium and uranium into the water. Though the immediate area is remote, currents could spread contamination. Danish authorities, who had not been informed that nuclear weapons were regularly flying over Greenland, protested the accident and demanded explanations. The revelation that Chrome Dome missions routinely carried nuclear weapons over Danish territory created a political crisis. Denmark's parliament demanded assurances that nuclear weapons would not be flown over Greenland in the future. The political fallout from Thule contributed to the eventual termination of Chrome Dome. Combined with previous accidents at Palomares and Goldsboro, the Thule incident demonstrated that airborne alert with nuclear weapons was too dangerous. By early 1968, the risks clearly outweighed the benefits. On January 28, 1968, 1 week after the Thule crash, Secretary of Defense Robert McNamara announced that Chrome Dome missions would be terminated. Henceforth, no American bombers would fly airborne alert with nuclear weapons except in extreme crisis situations. The era of 24-hour nuclear patrols ended at Thule. The timeline of what would have occurred if any of the 4 bombs had achieved nuclear detonation near Thule can be calculated from weapons effects data for a 1.45 megaton ground burst. Second 0. B-52 warhead detonates on Arctic ice 7 miles from Thule Air Base with a yield of 1.45 megatons. The fireball reaches a diameter of 1.8 miles and a temperature of 100 million degrees Celsius. Second 1. Thermal radiation ignites everything flammable within 20 miles. Thule Air Base, 7 miles from ground zero, experiences thermal flash sufficient to cause third-degree burns on exposed skin and ignite wooden structures. Second 3, the blast wave expands at supersonic speed. At 7 miles distance, overpressure exceeds 3 psi, sufficient to damage buildings and cause casualties. Thule's above-ground structures are heavily damaged. Windows shatter, non-reinforced buildings collapse. Second 15. The fireball rises, creating a mushroom cloud that reaches an altitude of 60,000 feet. Radioactive debris is lifted into the stratosphere. The stem of the cloud is 3 miles wide. Minute 5, fallout begins descending. The Arctic wind pattern carries radioactive material southeast across Baffin Bay toward Canada. The fallout plume extends 100 miles downwind. Minute 30. Heavy fallout is depositing across northwestern Greenland. Anyone outdoors receives dangerous radiation doses. The BMEW's radar installation at Thule, critical to American early warning, is contaminated and potentially non-functional. Hour 2. Thule Air Base has been effectively destroyed. Casualties among the 3,000 military personnel and 2,000 civilian workers approach 80%. The base's strategic radar systems are offline. America's primary early warning of Soviet missile attacks from the north is blind. Hour 6, fallout has reached Canadian Arctic settlements. Grise Fjord and Resolute Bay, Inuit communities with populations of several hundred each, are experiencing dangerous radiation levels. Day 1. Immediate casualties from blast, thermal and prompt radiation effects at Thule, approximately 1,500 to 2,500 dead. Fallout casualties beginning across northwestern Greenland and Canadian Arctic. Week 1. Fallout casualties increase. Estimates, additional 500 to 1,000 deaths from acute radiation syndrome. Thule Air Base is uninhabitable. BMEW's is offline indefinitely, creating a strategic vulnerability in American early warning. Month 1. Long-term contamination makes northwestern Greenland and parts of the Canadian Arctic uninhabitable. Approximately 5,000 people are displaced. The geopolitical consequences of a nuclear detonation on Danish territory are catastrophic. Year 1. Total deaths, 2,000 to 3,500. Thule Air Base abandoned. BMEWS relocated. Denmark withdraws from NATO. The political fallout from an American nuclear weapon detonating on Allied territory creates a crisis in the Western Alliance. This cascade would have resulted from smoke in a B-52's cabin, not enemy action, not a deliberate attack, just a fire that forced a crew to abandon their aircraft, which crashed and scattered 4 nuclear weapons, one of which detonated. The Thule accident forced comprehensive changes in nuclear weapons safety and operational procedures. The immediate response was the termination of Chrome Dome, but the broader impacts extended to how nuclear weapons were transported, maintained, and secured. The specific changes included: end of airborne alert, Chrome Dome terminated. No nuclear weapons would be flown on routine patrols. Bombers would remain on ground alert, ready to launch within 15 minutes, but would not carry weapons during peacetime flights. Enhanced fire suppression. All aircraft carrying nuclear weapons received upgraded fire detection and suppression systems, particularly focused on crew compartment heating systems, improved weapon security, enhanced physical security features on nuclear weapons to prevent dispersal of fissile material even if conventional explosives detonated. Environmental safety. New protocols for cleanup of plutonium contamination following accidents, international notification, agreements to notify host nations about nuclear weapons transiting their territory. The crew members who survived the Thule crash faced varying outcomes. Major Curtis Tully, the pilot whose decision to order evacuation saved 5 lives, continued in the Air Force and eventually retired as a colonel. He rarely spoke about the Thule incident, but in a 1985 interview stated, "We did everything right. We followed procedures. We evacuated when it became clear we couldn't land. But John Haug, Captain Svitenko, and Sergeant Snyder still died. And 4 nuclear bombs ended up on the ice. Sometimes doing everything right isn't enough." The political consequences for US-Danish relations were significant. Denmark had allowed Thule Air Base under the understanding that no nuclear weapons would be permanently based on Greenland. The discovery that nuclear weapons routinely flew over Greenland violated this understanding. Danish Prime Minister Jens Otto Krag demanded explanations and assurances. In 1995, documents declassified under the Freedom of Information Act revealed that the United States and Denmark had reached a secret agreement allowing nuclear weapons transits over Greenland, despite public statements to the contrary. The revelation caused a political scandal in Denmark and led to formal apologies. The environmental legacy of Thule remains controversial. The official position is that all plutonium contamination was removed during the 1968 cleanup. But studies in the 1990s detected residual plutonium in sediments near the crash site at levels above background. The long-term environmental impact is considered minimal but not zero. The question of the fourth bomb continues to generate speculation. If a complete weapon remains on the seafloor, it poses minimal immediate danger. The plutonium and uranium are contained within the weapon's casing. Corrosion will eventually breach the casing, but this process takes decades. Regular monitoring of the area has not detected elevated radiation levels, but the symbolic significance of a lost nuclear weapon off Greenland remains. It represents the imperfect control humans exercise over the most destructive weapons ever created. Even with safety systems, protocols, and trained personnel, accidents occur. And when they involve nuclear weapons, the consequences can be measured in plutonium contamination that persists for millennia. The statistics of what was prevented by the B-28 safety systems are significant. Date of incident, January 21, 1968. Initial smoke detection, 15:30 hours. Emergency declared, 15:32 hours. Evacuation ordered, 15:42 hours. Crash, 15:46 hours. Time from smoke to crash, 16 minutes. Location: 7 miles southwest of Thule Air Base, Greenland aircraft B-52G Stratofortress. Tail number 580256. Weapons: 4 B-28Fi thermonuclear bombs, 1.45 megatons each. Total yield aboard 8 megatons crew. 6 ejected successfully, 1 died from injuries, 2 died in crash. Bombs detonated, conventional explosives. 2 plutonium contamination, approximately 2,500 feet radius. Cleanup duration: 7 months. Personnel involved in cleanup: 1,700 contaminated material removed, 10,500 cubic yards. Fourth bomb status: unlocated, possibly on sea floor if weapon had achieved nuclear detonation. Yield 1. 45 megatons, 97 times Hiroshima. Distance to Thule, 7 miles. Thule personnel at risk, 5,000 blast casualties, 2,500 to 2,500 immediate deaths. Fallout area, 100 plus miles downwind. Strategic impact: loss of BMEW's early warning radar. Political impact: NATO crisis, possible Danish withdrawal. Environmental contamination: northwestern Greenland, uninhabitable for decades. The Thule accident demonstrated that even with multiple safety systems, nuclear weapons in routine operations could fail. Catastrophically, the fire that forced the crew to abandon the aircraft was not predictable. The impact forces that detonated 2 weapons, conventional explosives, were within possible accident scenarios, but not expected. The dispersal of plutonium near a populated base created exactly the contamination scenario that safety systems were designed to prevent. On January 21, 1968, at 15:30 hours Greenland time, B-52 pilot Major Curtis Tully smelled smoke in his aircraft's cabin. He had 7 minutes before his aircraft would crash onto Arctic ice, scattering 4 nuclear bombs and contaminating the area around Thule Air Base with weapons-grade plutonium. Those 7 minutes were not enough to save his aircraft. Not enough to prevent the crash, not enough to keep the bombs secure, but they were enough to save most of his crew. 6 men ejected, 5 survived, 2 others died, but the majority lived. The B-52 pilot smelled smoke over Greenland and had 7 minutes before 4 nuclear bombs hit Arctic ice. He used those minutes to fight the fire, declare an emergency, attempt a landing, and ultimately order evacuation. The aircraft was lost. The mission failed. Nuclear weapons were scattered across sensitive territory, but most of the crew survived, and the nuclear weapons did not detonate. The safety systems, designed to prevent accidental yield, functioned as intended. The thermal batteries were not armed. The firing circuits did not complete. Despite catastrophic impact, despite 2 weapons having their conventional explosives detonate, the physics packages did not achieve criticality, but it was close. Plutonium contamination, 7 months of cleanup, questions about a lost bomb, political crisis between allies, environmental concerns persisting decades later. All because smoke filled a B-52 cabin over the Arctic, and 7 minutes was not enough to prevent disaster. The smoke over Greenland taught a lesson: nuclear weapons in routine operations are never routine. Chrome Dome ended at Thule. The era of airborne nuclear alert terminated because the risks demonstrated in smoke and fire and plutonium on Arctic ice exceeded any strategic benefit. The B-52 pilot smelled smoke, had 7 minutes, made the decisions trained crews make. And most of his crew survived. But 4 nuclear bombs hit Arctic ice, and the contamination they left remains a reminder that 7 minutes is not enough when nuclear weapons are involved.